I wanted to make sure that somebody was talking about things that for beginners to Accumulo, or even people who have worked with Accumulo for a while but are maybe facing a new challenge, a new type of data, a new application, had a sense that folks like that were able to get a sense for how those of us who've been working with Accumulo for a long time kind of think about these different options that you have in the space of all the different tables that you can design. So one of the things about Accumulo, the good thing and the bad thing, is that it gives you a huge amount of control over how your data is laid out and how you build your application. But that also comes with a price. It can be hard sometimes to know how to get started. It can be difficult sometimes to map data that's out there to the Accumulo data model. And the Accumulo data model itself might be somewhat new. It might be something that you're not used to thinking about, how everything's sorted, but then you have these hierarchies. And so I want to kind of go through, kind of propose a new way of thinking about the pros and cons of different designs so that you can kind of verify that not necessarily verify, but justify the design that you've chosen and why you've chosen it. And the experience that a lot of people have is like, well, this is great. I went through the trouble to install Accumulo, and I've got some data and a problem. Like, now what? Now what do I do? And with Accumulo, the answer is you got to start writing Java code. But even before you do that, you got to think about how am I going to, for my application, how am I going to populate, what design am I going to use for my Accumulo table such that by the time I start writing code and by the time I start testing my code, my data is all laid out the way I want it to, and it's going to support the kind of queries I want to do. So you're facing like this huge space of things you can try, and there's not a lot of like obvious, in my opinion, ways of going about it. So I'm proposing a new way of thinking about these problems, which is trying to balance these 5 different things you might care about in your application. So one's query speed. That's just how fast do the queries that your application is going to be doing most of the time, how fast do those run? Not all the queries that you can possibly think of, just the ones that your application needs to do that you know about now. How fast is that? And with Accumulo, the goal is always to be able to support interactive applications. Interactive means that your application has to be responsive enough for users to ask a question, get an answer before they kind of lose their train of thought or get up and get a cup of coffee. So query speed is really important, and you'll see that in all the designs that we talk about today, that one's going to remain important. Now the other ones are things that you might decide to trade off. And it turns out, in fact, that there is no perfect design, at least that we've found yet, that maximizes all 5 of these. So it's kind of like a 3-sided sheet, and you're trying to make the bed, and like you keep pulling it, but one of the corners always keeps getting exposed. And you'll actually like see that with this little diagram. There's no design that really perfectly touches all 5 of these points. You're going to have to make trade-offs. But the good thing is, if you know what you care about, and you know that you're able to sacrifice one of these things, you can probably maximize the other dimensions. So if you're familiar with the CAP theorem, it's like you can have 3 properties in a distributed system, but or the 3 possible properties, but you can only have 2 at a time. This is kind of the same thing, but I'm saying there's kind of 5 properties out there that you may or may not care about, but you can't have them all at once. So, but talking about like how these things trade off and why is what we'll be getting into. And so query power, well, I guess I'm going to define these. Here we go. I'll define all these dimensions. Query speed is how fast the queries that you want to do, how fast they run. Concurrency is how many users can query the table or the cluster at the same time. Query power is how many different queries are supported without having to do like a table scan. Which again, if you do a table scan, you've completely lost your query speed, right? You've lost your interactivity. So query power is like how expressive or how flexible are the types of queries you can do. Atomicity, that's how easy it is to change a value without creating an inconsistency. So if you're not doing any updates at all, and you probably don't care much about atomicity. You might care about all the data getting to the table all at the same time. But if you're not doing any changes that can create inconsistencies, then atomicity is easy. But if you are doing updates, then what you want to have is you want to avoid inconsistency as much as possible. So again, if this isn't, I guess, maybe perfectly clear, in traditional databases, you tend to normalize tables, which means you try not to have or one thing stored in two places at once. So for example, I don't want to store my phone number along with all the orders that I've made to a particular company, because then if I change my phone number, I'm going to have to potentially go back to all those old orders and change my phone number in a bunch of different places. And it might be that somebody does a read while I'm in the process of changing my phone number and gets my old phone number, right? Or gets worse, sometimes you can do a read and get two different values for things you think should be the same. So there's lots of ways this can happen. Anyway, atomicity is the property that everything that you change, everything you want to change changes all at once. So that how you design your table is going to affect that. Finally, ingest speed. That, I guess atomicity is a complicated one. Ingest speed is just how does your table design impact how fast you can ingest your data. So without further ado, we're going to jump in to a couple of table designs. Now, I call these design strategies, not just table designs, because table designs are very specific to an application. But an example of a strategy is like an approach to several table designs that all kind of have the same properties. So that'll become, I think, clear here in a second. Well, one thing you find out, though, is when you start working with real-world data is you've got all these relationships. And like, if you try to model those as in a traditional entity relationship diagram, you find out that there's kind of a lot of complexity there. It's not just a simple tree hierarchy, right? You've got many-to-many relationships, and you might have circular relationships. And so when it comes time to using Accumulo, Accumulo is designed, its data model is designed such that it supports storing obviously very many rows, and each one of those rows can have very many columns. And it actually, Accumulo tables don't have to just store what you would normally store in one table in a relational database. You can actually support some types of one-to-many relationships in a single Accumulo table. The reason you can do that is because you can use column families and column qualifiers in such a way that, so for example, if I had two phone numbers, I could just store that in a single row in Accumulo if I wanted to. Whereas in a traditional database, you'd have to say, well, there's the customer record, and then there's a relationship to how many phone numbers you can have. Traditionally, if you're doing like the typical normalization in a database, you would split those into two different tables. In Accumulo, you can actually combine those. But you can't go much farther beyond that. So hopefully you'll see what I'm talking about here in a second. So this Accumulo data model looks like this. You can have rows, and each row, a table consists of many rows. Each row can have many column families. Each column family can have many qualifiers. And then glossing over column visibility and timestamp. But basically, a simple way of thinking of this is that each unique row, family, and qualifier has one value. So you can see how there's this natural hierarchy there. So any kind of one-to-many relationship that might exist in your entity relationship diagram should fit nicely into here. I think typically what a lot of people do with this is they'll take it and they'll try to pull out the views into this diagram that all look like trees, and then they'll create a table for each of those. So I'm going to try and make this more concrete. This is basically a single table strategy where you can have something you care about, like a user of a website, and then you can have like different things you store about that user. You can have all the orders that they've made, and then maybe details about the user. So there's lots of there's like a one-to-many relationship here, obviously, between users and orders. Orders themselves may have a one-to-many relationship between, you can order multiple items on a single purchase. And then you might store some information about that, like how much the actual item cost when you made that order. So you can see I'm stuffing more than just a 3-level hierarchy into the Accumulo data model. In fact, I've got users to orders, and then orders to items, right? So I'm kind of doing branching twice. And then when it comes to user details, that's, I guess, fairly straightforward. But like I said, you might have like multiple phone numbers. So you can do this kind of stuff in a single table in Accumulo. And as long as you're accessing this table in one or two ways, then your performance is going to be good. So for example, if I'm always looking up a user by his user ID, like user A, then my lookups are always going to be fast. But even if I want to do something like, say, well, I want to scan over across several users, but I only want to pull out their phone numbers, that's also reasonable to do, because you can use things like Accumulo locality groups to scan across a subset of columns. So hopefully, I'm not moving too terribly fast for beginners in here, but Accumulo is row-oriented primarily. You can, however, decide to store different column families in different parts of the disk. So if I want to scan over the details of all my users, I can do that without reading all the orders data off of disk. That's a feature called locality groups that Accumulo has. So that's kind of two types of queries I can support with this one table. It's easy and fast to get all of users' information. I can also relatively easily scan over multiple users for just a particular column using locality groups. But there's other things that are going to be very slow. If I want to figure out which users bought a particular item, I have to scan the whole table, right? And again, so that's going to be slow. So I've lost my query speed. Looking for which items are over a certain price requires a table scan. And then I pointed out how I was starting to kind of double up on my dimensions, where the column qualifier was kind of storing 2 dimensions for me. It was storing orders and their ID and their items. So order ID 1 and the first 2 column qualifiers kind of logically belong to the same order, and then the third one is a new or different order. Okay, so that's kind of the simplest table strategy that you can that most people start with, and then they rapidly. I can't even tell you how common it is for users to run into this and then say, yeah, but I want to look up, who bought a particular item, and now I'm doing table scans, and they'll ask me, like, is there any way I can like rearrange it somehow to like support all those queries at once? And there's just like no good way to do it, right, with one table. And sometimes you get in this, you try and spread the pain, so none of your queries are fast, but they're all like, none of them is like too terribly slow. And anyway, the trade-off you end up facing is you get this kind of a performance profile. Query speeds for the queries you are designing, like looking up a user or maybe looking up just user details, those are going to be fast, like as fast as it gets. And by fast, I mean sub-second, like ideally low numbers of tens or, ideally less than 100 milliseconds, low tens of milliseconds. Your ingest speed is going to be fast because you're only writing the data down once and in one single way. Atomicity is good because Accumulo gives you control, it gives you row-level transactions. So I can change both the address and the phone of a user at the same time, and you're never going to see a partial update. So that's great. Concurrency is great because each query is going to go to a single server and fetch a very small section of the tablet and read it back to the user. So that means I could have thousands of people querying this table at the same time, all with good performance, and I'm not going to run into any problems. Where I'm really falling short is in my query power. So I can only do 2 kinds of queries efficiently. And it turns out that some applications only need 2 types of queries. And if that's the case, then you're done. And good for you. And there's a lot of applications at Google, I think, that just work like this. And they work great. Scale to millions of users worldwide. But usually what people run into is they say, that's just not enough query power. I got to have more query power. So when you start tugging on that edge of the sheet, the other corners are going to start pulling back. And the way they pull back and whether or not they pull back in a way that's acceptable to you is up to you. So we're going to talk about some other things you might do. So you might say, well, I like my single table strategy, but I do want to do some special lookups. So I'm going to store my data in two ways. So I'm going to store the user details, here, the user's phone number here this way, so I can look up a user's phone number starting with the user. But then also, I'm going to store it backwards, so I can find out for a given phone number who owns it. And I'm also going to store these things. A particular item was bought by a user and how many times. So you can start adding some what I call inversion. So you're inverting the order of these key value pairs, or these row column qualifier values, tuples. You can start inverting those, and you can even store those in the same table without causing that much difficulty. You do want to make sure that your maybe namespaces are separated. So here you might prefix a phone number with its type, so you know that the phone number is different than like the amount of an order or something, if there's a chance for collision. But this is trying to directly address that problem of I'm not able to do some of the lookups that I want to do. So if we think about this one, it's easy and fast still to get all users' information, can still scan for specific columns, but now looking who bought a particular item is fast. There's certain things that are still slow, like if I don't store inverted information about the price of items, I still have to do a table scan. So whatever you decide to invert is going to be fast. Whatever you don't invert is still going to be slow. But now I have this new problem where I've lost some atomicity. So updating user's phone number now has to be done in two places, which you might say is acceptable. I have to do it here, and I got to do it here. And Accumulo, remember, doesn't have multi-row transactions. So you have the chance to introduce some inconsistency and expose that to your application. It may not be a problem, but it's something you should think about. So performance profile-wise, it's going to look like this. You're sacrificing a little bit of ingest speed because you're writing more key value pairs now. Your query speed's still great for the queries you want to do. Your concurrency is still pretty good. You've lost some atomicity, but we've increased our query power. So we pulled the sheet down and to the right, and we lost a little bit on the lower left-hand corners. Now that's pretty good, though. I mean, you're getting pretty close to like the ideal pentagon shape there. And these are all estimates too. Like I didn't do any rigorous testing. I was just thinking, all these scores go from 0 to 10, and 10 being like the best you can do, and like 5 being half as good as the best you can do, and then 0 just being completely worthless. Okay, so now that you kind of get what I'm doing here, I'm going to move a little bit faster. So now you can say go whole hog and say, forget it. I want way more query power. I want to be able to query on everything. So you can build a completely separate table and treat it as a secondary index, where you basically take the contents of your first table and you flip it. But notice I'm now just giving up on querying the first table. I'm saying, why do I need to make the first table queryable if I can query everything using my index, right? So you change the first table to have unique record IDs. You store your fields in a very regularized way, which you can see now I just have fields. And then I just have the name of the fields. Notice that I'm starting to like double up some values, though. But these are things that had a one-to-one relationship before, so that's OK. And now I have an index that takes these values and makes them into row IDs. And I have column families and column qualifiers and no values over here. This is because you need to be able to store potentially multiple records for a single value. So you need to put those in the column qualifier so you can have multiple of these. Anyway, this gives you a different performance profile, right? Now you can look up records using any value in any field. But every query has two steps. You've got to look it up in the index and then go fetch the records that match. So if I say, give me everything that's $5, it'll say, OK, there's 2 items that are $5, the records A and B. And you can say, OK, well, there they are. Indexing everything, though, would decrease ingest speed by roughly, like I'm storing everything twice now. So your ingest speed might be cut in half potentially. Now, in practice, you get crazy good compression on the index. Like I've seen indexes of 1 billion records where each index entry takes up 7 bytes, which is incredibly good. Your mileage is going to vary, but you get some great compression characteristics. Now, your updates, though, are going to be a lot tougher. Because you're going to, if I change one record, I might have to go in and change 4 index entries. And there might be ways your application can manage that. There might not. But these are different tables. And so you're coordinating, your application is going to have to coordinate these changes. Could you use something like Fluo to manage these changes? Absolutely. But you're still going to have the potential for somebody doing a read. Let's say I find that a certain record has a certain value, and then I go to look for that record, and that record's been changed. You want to avoid that type of scenario. You might be able to avoid it by changing your index before you change your record, but it's not necessarily guaranteed. Each query still involves few machines, so your concurrency is going to be good because you do a very minimal scan here. You can get a relatively small number of records, ideally, and then you can batch scan those. So it's a little more expensive, but the concurrency is still going to be really good. So your query speed is really good, but now it's a 2-step thing. In practice, it's pretty good still, to the point where I would say 90% of the best. Concurrency is still high. Ingest speed has been halved. And atomicity has gone down by quite a bit as well. But your query power now is way out there. Now, when I say your query power isn't 100%, that's because there's certain things that are hard to do with a secondary index. Like, for example, if you wanted to add 2 things that had incredibly, that were very popular in your data. So I want to look for the White House. The is going to be an incredibly popular term, and then if I want to intersect that with a set of records that have the word house, that's going to be a large number of records. So as your queries get more complex, they're still very flexible. I can query on any single field, but the complexity of my queries is going to be limited somewhat. Nested ands and ors and things like that are going to be harder and harder to implement, but still pretty good. So if that's as much query power as you want, you can get it by paying for it in ingest speed and atomicity and a little bit of query speed. So this is how you can think of these things. Like a move in one dimension is going to cost you in a couple other dimensions. And if you're happy paying that price, then good for you. OK, so moving further down the field, embedded indexes. So I'm calling these embedded indexes. But other people might call these document partitioned indexing. Or Adam Fuchs gave me a really long way to say this. Document distributed information retrieval strategy system. Depends on how much you're trying to impress your audience, I guess, or put them to sleep. So in this scenario, you have, oh, I should have removed the word table from that. I meant to do that. You have one table again, but you have kind of 2 sets of records. So your index is living with your, so instead of partitioning across 2 tables, I'm just going to partition by record. So I'm going to take a record and all the index entries that belong to that record, and I'm technically going to store them under the same row ID. And I'm not showing that here, but that's the gray bar is showing the grouping. The advantage of this is I can do some pretty complex query operations on that index, like really complex ands and ors, and answer the question of whether or not record A matches my crazy complex query. I can do that all locally on the tablet server. And then the tablet server makes a decision whether or not to send record A as a result. So you eliminate a lot of the problems you have with secondary indexing, and you really blow out your query. You really have great query power. The only thing is, now you're not sure which records are going to match. You don't know where to go in the index to find exactly what you want. So in this index, if I want to know which items cost $5, it's easy. I just do a single lookup for the $5 in this index table. Here, the index entries are not the rows in my table. So you have to send the query to potentially naively every tablet server in your cluster, and then ask them, for all the documents you're in charge of, do any of them match this query criteria? And then go to the next one, for all the documents you're in charge of. And so you can do that all at once. If you do, though, if you do, then each query involves many machines, which sacrifices concurrency quite a bit. So you're throwing a lot of hardware at every query, which means you can do less queries per cluster per second. But you can still quickly look up records containing any value in every field. It's still a two-step process, but it's done within each tablet server. The indexing speed is the same as for secondary indexing, I would say, just the same storage. But now index entries are located with documents, so updates can now be done atomically again. So now if I actually change the cost of an item, like in this order, I can also change its index entry right there. And if these live in the same row, I can do it atomically. So that's pretty cool. You gain that back. So this one, I think, has the kind of weirdest performance profile of all of them. Your query speed is gone down a little bit just because you might have to wait for the answer to your question might be on like only that tablet server way over there, but all the tablet servers are working. Your index speed's the same as before with the secondary indexing. Your atomicity's back, boom, you can change anything. Your query power is just totally through the roof. You can ask arbitrarily complex questions till the cows come home, and nobody's, you're not going to be penalized for like incredibly complex queries. Your concurrency is a disaster, however. So it's a little bit awkward. However, if you don't have a lot of users and you do have a lot of updates and you do have really complex queries, maybe this is the strategy for you. Finally, I came across an interesting design when looking at how Cassandra implements their secondary indexing, which is instead of naively, oh man, this is a crazy slide. I didn't mean it to look this crazy. I don't know. I don't know what's going on with that index. Imagine that you've got a lot of servers. So say this is one server, and it's got two partitions in it. You may have multiple servers, right? And so I said that in this embedded index strategy, you have to query all the servers at once. Well, you actually don't have to do that. And what Cassandra does is it'll go out and just start at a random partition, at a random server, and say, for all the documents you are in charge of, do you have any that match this search criteria? And if the answer is yes, and it actually fills the first batch that the user wants, like say he wants to see 100 results at a time, then you just answer the question, and you don't have to ask any other servers till the user comes back and asks for more. So they do this but if they don't find what they're looking for at the first server, then it says, okay, well, there may not be very many documents out there like this. That's a strong assumption because depending on how you distribute your documents, usually you do it in kind of a randomized fashion. So you should have a roughly uniformly random sample of documents in each partition. So if you look in the first one and you find nothing, then there's a good chance that the number of records is going to be low overall. So what Cassandra does is it looks then, instead of querying just the next tablet server over, it queries the next 2 tablet servers over and say, oh crap, we've got to search faster. We've got to throw more resources at this because the answer might be hard to find. And then if that comes back, it doesn't have enough results, then it sends the query to 4 more tablet servers and so on. And so worst case scenario is there's no results, and you have to and just look across your whole cluster faster and faster and then find out there's no results. But that way you can at least kind of, if there is only one result and it's way over here, you'll get there eventually, and it may still be interactive. So this is interesting. So each query does involve many machines, but much less than before. So you gain back a lot of this concurrency that you lost. And now it's looking a little bit more, remember, the ideal shape is like this nice full pentagon is what you want. So just to kind of compare all those to each other, depending on what you really care about, these are some real popular query strategies table strategies that we've seen. Now there's a lot of tables out there that are maybe a subset of these. I was trying to think of where D4M would fit in here. And I think D4M would actually fit in the sum inverted or the secondary index because it has 2 tables. One is just a transpose of the other, and it's just storing triples. And then at that point, all the queries you want to do are fast. So even if you don't think one of these tables or your table design fits in here, it may just require blurring your eyes a little bit maybe and figuring out what's going on. But I like this because it kind of helps you understand why a particular table is going to be good for your use case or maybe not. And it also highlights a problem that I see in general with people going to NoSQL, which is they invariably jump to the single table design first because it's the easiest to implement. The other thing I should mention, these are all growing in complexity in terms of implementation over time. Like this one requires just more code than this one. It's just more complex. So you don't necessarily want to jump to this because it's fancy, but you don't necessarily want to start out here knowing that your query power is just going to be inadequate. So don't even waste any time over here if you know that you need more than a small handful of queries you need to support. Because mostly what I see is people that get stuck right here and they're like, do I go here? Do I go all the way over here? Like, I don't know what to do. I think it's much better in the beginning to admit whether or not this is going to happen, is going to be adequate for you. And then if not, just say, okay, let's really bite the bullet and think about how many inverted entries we need. Do they fit in the same table? Do we need a separate table? If we're talking about a separate table, how important are updates, right? I mean, you can almost build a flowchart from this. I'm probably going to try and do that later, add it to these slides. So hopefully this has been helpful for folks to think about. This is kind of a simplified flowchart. Think about how many queries you need to support, how frequent are your updates, how many simultaneous users do you expect, and then how is that going to impact your ingest. I think ingest is the easiest one to account for because you can just grow your cluster if you really need to. But the other things are a little bit harder to address outside once you've decided on a table. So, and that is, I think, time. Any questions about that stuff? Yes? Process. Yeah, that's a really good question. I should mention maybe the simplest thing, which wasn't on your list yet, which is just, well, there's two things, I guess. One is your application can handle it. So you might not have to rely on a back-end update or trigger mechanism to do that. Your application itself could just say, I've got a new record, update the index entries, and then write the new record. Your application could try to manage that. The other thing is not all applications have live writes. So sometimes you ingest records in a batch way. And if you do, what you can do is ingest your records and create R files for those records. And at the same time, create the corresponding index entries. And only after the index entries are created and are intact, if that job completes successfully, then you can bulk import that data into the table effectively at the same time. So you eliminate the possibility, the window for this inconsistency. Again, that comes at the cost of latency if you have to build your index entries and your record R files all at the same time before you can query them. But a lot of applications are like that. So historical data, obviously, if you're loading that. But if you're loading it live, you can try and address it with your application. So you can, and again, you might want your live updates to be batched anyway with a batch writer. And so you can do things like there's actually a multi-table batch writer in the API. And there's ways you can call flush on that so that they flush both at the same time. And then if you get a problem with one, you can try and retry the others to eliminate inconsistencies from failures to write to the index table or vice versa. So the API has some options for that too. I would exhaust those before I looked at things like, unless you know you're going to have a high rate of updates or you have really low latency requirements. But it's not clear necessarily that Fluo is going to be any faster than something you do in your application. The nice thing about Fluo is you can have these cascading events happen, and once you solve that problem once with Fluo, you might be able to have many applications take advantage of it. The one thing also that's nice that's not on your list is doing it with iterators. I think people used to try that and say, can we do writes to another table from an iterator? It's like, there's a lot of reasons you don't want to do that. So looking at things like Fluo for that, those really just depend on your updates and your latency and things like that. So don't forget about the first two things. So I guess the other thing is if you use an embedded index strategy, you don't have to worry about that cascading update problem, because when you write a new document or an update to a document, you're writing the index entries too. And so you do get that atomic update for all your documents and all your index entries at the same time. That to me is the like primary advantage of that that design. That and your query complexity is essentially unbounded. But that's a really nice property to have, I think. Yeah, that's a good question. So if you just can't get enough Aaron Cordova today, I'm going to give another talk at the end of the day about HBase versus Accumulo versus Cassandra. And Cassandra actually has some secondary indexing built in. So it actually resembles something like the embedded index. Actually, it's like I said, is closest to the embedded index with round strategy, except for they do have some shortcomings, in my opinion, compared to how you could implement it on Accumulo. So, but Cassandra does it just fine, and Cassandra is a very popular database. And they have a very high-level query language on top. And so I don't see any reason why Accumulo couldn't have something like that built on it. The question whether or not it should be built into Accumulo or over Accumulo is one that's, I think, up for debate. Cassandra has built it into the database, and you can no longer use any other APIs, as far as I know. They have a deprecated thrift API. So I don't know if we will want to necessarily do that, but like I say, it's up for debate. But I think having these capabilities and not having to recreate the wheel every time is fine. I mean, it's a great idea. So yes, I think that's a great idea. I'd love to talk more about that. Cool. Thanks, everyone.